You know, I'm at some random place in what we were talking about on Friday, but I just wanted to remind you of the two big facts of the first part of this chapter that we're going to be using. And that is what's in red down at the bottom of this, which is at sort of a random place in here. What we figured out is that when an object is in uniform circular motion, that means moving in a circle at constant speed, the acceleration is a vector. It's always a vector. Points toward the center of the circle when you're in uniform circular motion. And its magnitude is v squared over r, where v is the speed you're moving at and r is the radius of the circle that you're on. And we were doing some problems with it. We did one that was sort of easy. This was one where someone's in outer space and the only force on the object moving in a circle was the string tension. So that one was pretty straightforward. And then we did a more complicated kind of problem, which was I called the conical pendulum, and that was something moving in a circle. Circle is a horizontal plane. Maybe those of you who are at home, I haven't unshared this, but you might be able to maximize my video window. This little mass is moving in a circle at a constant speed, but the tension is not directed towards the center of the circle. Neither is gravity, and the only forces on this mass are the tension and gravity. And so in order to use the fact that the magnitude of the acceleration is v squared over r, we made sure to choose one of our axes pointing in the known direction of acceleration. So we drew a little free body diagram at this particular location here, just in the cartoon. And we've got a tension and we've got gravity. But I know that the acceleration at that instant points toward the center of the circle, directly to the right in my diagram. And so it made sense to choose the x-axis maybe to the right and then y vertical. Otherwise, you might have been tempted to choose tilted axes or something, right? At least one of the forces is tilted. So we were able to figure out what the acceleration magnitude is. How fast is it accelerating when it's moving in a circle? Notice we weren't given anything about the speed, right? I can't necessarily just do v squared over r. I might have enough information to get r, but I don't know what the speed is, but we'll figure that out later. Just by doing the sum of the force x components, and one of the things I want to emphasize at the end is when you want to use F equals ma, you've really got to do a free body diagram, and you've got to put axes next to it. Otherwise, it could be a total disaster. And that happened in some places on the exam where people were using F equals ma. They didn't even put the subscripts on. I don't know what components I'm using, but this is only true for components of forces. And so in order to know what the components mean, I've got to have a free body diagram and I've got to have axes next to it. So I know what the x component of this force and this force is. This one's x component is 0. In any case, by doing F sum of the force x components equals max, we said, well, we weren't really lucky. I could have found the magnitude of the acceleration, but I didn't know what t was. T was partially along the x direction. So then we did y components. T cosine 35 comes in with a plus sign for the y direction, and the weight comes in with a minus sign. And another thing to emphasize is that you only use y components or only use x components in one equation. You never mix x and y components. That was something that I saw some of on the exam too. That allowed us to solve for the tension and then allowed us to solve for the acceleration. I mean, it's not so amazing. It's a little bit less than little g, but you're going in a circle, so it doesn't feel like free fall acceleration here. And then we could find the speed that it's going at just by knowing this little bit of geometry here. We could figure out how fast it had to be going. Once we know the acceleration, we just set that equal to v squared over r. So 6.86 in SI units is v squared over r. And r, you know, the sucker answer for r is 0.5 meters. Why isn't that the r that goes in v squared over r? Yeah, or it's not the radius of the circle that it's traveling on, right? It is a length, but that doesn't mean it's, I have to look at the circle that the thing is moving on in uniform circular motion. And when I use v squared over r, I mean the radius of that circle. That's not 0.5 meters. I have to do 0.5 times the sine of 35. And then that's an equation, set that equal to the known acceleration, and then solve for v. Again, not a mind-blowing answer. Okay, in this case, you know, the thing is, we were talking last time about, on Friday, the word centripetal force. And sometimes people are tempted to think, oh, well, there's this new force we're learning about now. It's called the centripetal force. But there is no centripetal force. The only forces are the same ones we talked about back in chapter 4. We're going to add gravity into it, but it's not a centripetal force any more than anything else is. There's no one centripetal force. People tend to think of a centripetal force as something that somehow mysteriously points toward the center. But notice, the centripetal force is nothing but the sum of these two vectors, right? We would just say it's the net force. The net force points towards the center of the circle, and therefore the acceleration is that way. There's nothing new or mysterious about moving in circles. It's just a special case of what we did before. Okay, and we ended last time right before I was going to hand out a worksheet to do. So let's try it, and we'll start it together, and then I'm going to have you finish it. But as always, it really helps once you've started to do a part to check with someone who's nearby. I know you have to be with, it's got to be someone in shouting distance because we're all spread apart, but it really helps to raise questions if you can talk with someone near you, or, you know, draw your free body diagram and then check, and then solve for the thing that's asked for, and then check with someone nearby you. So let's do A and B together. This again is a case where someone is sitting on this Ferris wheel, and the Ferris wheel is moving around at a constant rate. And so that means the person who's riding on it is executing uniform circular motion. But the forces that are acting on that person are not necessarily even constant in magnitude here. As a person is riding around, just to sort of set it up, what's, you know, at a random point on here, a person, let's imagine for the fiction of this problem that the person is sitting, their seat always stays horizontal, right? So these things sort of stay level as they go around. And what forces might be acting on the person at any random point in the ride as the person executes uniform circular motion? Just shout one out. Gravity, their weight force, right? Right. If you're near the surface of Earth, and well, it didn't say so here, but we're assuming the Ferris wheel is at the surface of Earth, and it, you know, the strength of gravity doesn't vary appreciably from the bottom to the top. We're assuming it's not, you know, as big as the Earth or something like that. So weight force is always pointing down towards the surface of Earth, right? So it points down at any point. What other forces might be exerted? Yeah, Arthur. The normal force, that's right. So there's an upward force from the seat. And there could also be a friction force from the seat, right? If you imagine, you know, usually we don't design Ferris wheels to go frighteningly fast. But if it were going frighteningly fast, you know, as you're moving around, you might find yourself sort of being pulled to one side or the other on the seat. And hopefully that friction force is keeping you on the seat. As you're, you know, going around, you're also being pulled left and right. What's going to do that? Well, it's not an upward normal force. If the seat is like this, it's not your weight force. It has nothing to do with left and right. So the friction force will have to kick in there. Okay, so here's the details. 15-meter radius for this rotates at 7 revolutions per minute. That doesn't sound very fast, right? 7 complete revolutions per minute, but we're going to find out that I made it so that it would actually be quite a fun and exciting ride to go on. If you have a big Ferris wheel, it actually takes a really long time to go all the way around, you know, in the times when it's moving at a uniform rate. Usually they're letting people on and off so often that you don't get very long at a uniform rate. 75-kilogram rider passes point A, that's rounding the bottom, then B, and then C. Those are just 3 different points they pass as they're in uniform circular motion. We're going to imagine the rider sitting on a scale that all their weight is on the scale. All the scale is the only thing pushing up on them and exerting friction on them. In other words, their feet aren't separately on the ground. They're all crouched on the scale, so that it can read their apparent weight. As we found out in the elevator problem, your weight isn't the scale reading isn't always equal to your real weight, right? When the elevator's accelerating up, the scale is going to read more. And when it's coming to a stop at a higher floor, it's going to read less than your weight. That's why the scare quotes are on there. Apparent weight, it's just not your weight. But people tend to call it your apparent weight. It's how heavy you feel. Like when you're in an elevator and it starts accelerating up, you feel like you're on a bigger Earth that has bigger gravity. And when you're coming to a top floor, you feel lighter. And so, that's why people call it your apparent weight. But your real weight doesn't change. What is the rider's real weight? Is A. I want to do A and B together. What's the rider's real weight? How do I calculate that? It's just mg. It's been a long weekend, just checking. The rider's real weight is just mg. 75 kilograms times 9.8 is 735 newtons. Okay, we're going to use that because it's going to be one force that comes into a free body diagram that we've got to draw, or we'll mess it up somehow. What's the rider's speed relative to the ground? Well, we did a little trick last time. I said, well, it's not really a trick, but I call it the distance over time trick. And that was the following. We're told that the person is going around at 7 revolutions per minute. And how did we translate that into a speed? Can someone remind me? That one definitely needs to go in the trash. How do I translate that 7 revolutions per minute into a speed? Yeah, Arthur. Right. So we said this is why I call it the distance over time method or trick, because if you're going at a constant speed, and that's what the uniform part of uniform circular motion is, you can use any distance as long as you use the corresponding time, or you can choose any time as long as you use the corresponding distance that you move through or the object moved through. So I've taken down the problem, but you can see in front of you, we're told this is rotating at a rate of 7 RPM, 7 revolutions every minute. So it seems like a minute or 60 seconds, if we want to use SI units, is a good amount of time to choose. And then it's up to me to say, well, how far in distance does the person move around a circle in 1 minute? Well, they move through 7 revolutions. 7 revolutions is 7 circumferences. And a circumference is 2 pi r. So here's the distance they move through. 7 2 pi r's. And what was r in this problem? I think 15 meters. Is that right? So that's a good thing to remember. We're going to be using that over and over again. It will definitely, be something that shows up somewhere on your next exam, that distance over time trick. So, and we'll be practicing with it quite a bit. So that number ends up being 11 meters per second. So then we're asked in the next 3 parts, draw a free body diagram. I think the actual statement is a little bit different than what's up there. Draw a free body diagram for the rider at position A. That's the bottom. So the rider's rounding the bottom, frighteningly fast. Do you have a sense of how you would feel as you round the bottom? Would you feel normal in your weight, or would your apparent weight be bigger or less than normal? If you really whipped down by the bottom, but your seat stayed horizontal, would you feel heavier than normal? Do you guys have that intuition? Or lighter? Heavier than normal, right? It's the same, like I feel heavier when the elevator accelerates up, right? I feel heavier, like I'm crushed down to the bottom. It's the same way here. As I'm rounding the bottom, I'm accelerating up. So we're going to find out. You should find that your apparent weight, what the scale reads, is bigger than your actual weight, which is the answer to part A. And then, so we're supposed to answer, what will the scale read? That's the apparent weight. And what forces cause the centripetal acceleration? In other words, for the conical pendulum, the forces that caused it, I would say, was some combination of the tension force and the gravitational force. How large is the seat's friction force on the rider? Is there a friction force necessary on you as you round the bottom in order to keep you in uniform circular motion? So you're going to do A, then you're going to repeat for C, and then you're going to repeat for B as you're rounding the side there. So try those. I'll at least give you enough time to work on it so it seems like everyone's gotten through the first of those three parts, which is part C, which refers to position A, strangely enough. I'm going to put my answers up here for C, D, and E, at least the scale reading, just to start a conversation.
Dr. Kelly, could you repeat real fast? Where did you get the 7 for the velocity equation?
That's from the 7 RPM value. So when you think about the meaning of RPMs, RPM means revolutions per minute. So the person who's writing this goes through 7 complete revolutions every minute. So in 60 seconds, they go through 7 complete circumferences, 7 complete trips all the way around. Each one is 2 pi r. I'm relying on your high school or junior high geometry knowledge there. 2 pi r is the circumference. You ever need those kinds of things like the volume of a sphere or the area of a circle, just ask me during an exam even or something. I'll probably be very generous with that because it's not the main point of the course. Anyone having trouble getting started? Just trying to give you guys enough time so that it looks like most people are through the first of those 3 parts. And then we'll be doing something similar in D and E, although it ends up kind of different, as you can see. Okay, in walking around the room, most of you look like you're coming to the end of C and starting to work on D. The first thing I probably want to do in C, because I want to find a force, and forces are part of F net equals ma, and I know something about A for uniform circular motion. I probably am going to want to use F net equals ma, and that scale force will be something I can solve for that. And you absolutely don't want to do that without drawing a free body diagram. So I might draw a little cartoon. Here's our 75 kilogram rider rounding the bottom of the circle. And I'm going to draw as they're passing. I don't know if they're going to the left or to the right. We'll find out. It doesn't matter. But let's, to the side, draw a free body diagram for that 75 kilogram rider at that instant. Okay, we know there's a weight force, and we already calculated the weight force. It's 735 newtons, right? M times little g. We already did the work for that part, and that doesn't change. Doesn't matter how you're moving. The Earth always pulls on you with the same force as long as you're close to the surface of the Earth. When you get far away, it doesn't pull on you as hard. What other forces are acting on you? Well, the scale is probably pushing up on you, and that's one of the things we want to find out, right? I want to find out what the scale reading is. Oops, scale. What other forces? Well, there might be a friction force left or right. Let me put it in there and we'll be able to solve for it. You can see the answer is that it's 0, but I'm just going to sort of guess and say, here's F friction as I'm passing the bottom. Maybe. We'll find out. It's easy to show it's 0. Okay, step 1, got to have a free body diagram. Step 2, you've got to have axes on it, because if you're going to do F net x equals ma x, you need to know what x means, right? If you don't have any axes on there, you have no idea. Now, in this case, I probably wouldn't be tempted to tilt my axes, right? Because all 3 forces are horizontal and vertical. But our rule of thumb for how you choose whether or not to tilt your axes is what? If you know the direction of the acceleration, make sure one of your axes points along that direction. At this instant, which direction is the acceleration of the rider? Upward. It's toward the center of the circle. The rider is moving on a circle. So at this point, that's the direction to the center of the circle as you're rounding the bottom. So this is the direction of the acceleration. I mean, I could call it y, I could call it x. I don't really care. X, y. The important thing is I want to know F scale. That's the first thing that's asked. What does the scale read? And so we're going to do F net y, or the sum of the force y components, equals ma(y). And I've got to think carefully about the signs of these. Everybody okay that F scale comes in with a plus sign for y components and the weight comes in with a minus sign? F scale minus 735. And this one has 0 x component, so I don't need to worry about that. I'm sorry, y component. 0 y component. We're only talking about y components here. That's equal to the mass in the free body diagram times ay, and ay is minus 9.8, right? No, because the person would be in free fall if it were minus 9.8, but they're not in free fall, right? There are lots of other forces acting, so definitely not in free fall. What is the acceleration? V squared over r, because they're in uniform circular motion. We know the acceleration points up this way, so its y component should be positive. You got to think about that. Some people dropped a minus sign in some places on the exam, but this is a component. In my coordinate system, this acceleration is a positive y component. And the magnitude of it is v squared over r. And we just found out, if I put under here v squared over r, that's 11 squared over 15. Comes in with a plus sign, right? And the only thing to solve for is F scale. And apparently F scale is 1340 newtons, a lot bigger than the real weight, or the normal feeling normal weight, is 735. So this is quite a bit heavier than normal because we're going frighteningly fast. Yes. Yeah, the scale is providing the normal force. In other words, I'm sitting on it and it's pushing up and keeping me from falling down, or actually keeping me moving in a circle. I wouldn't be moving in a circle if it weren't for the scale pushing up on me. Yes. That's right. And the weight of this is a force with a negative y component. That's why I'm subtracting it. I'm adding in this is adding up a bunch of y components. This one's y component is negative because I chose plus y to be up. So you got to be very careful about those signs. In any case, this is what it is. I could do the same thing. So I haven't answered about the friction force. Let's do friction force is involved in the x direction. So let's, of course, do the sum of the force x components equals max. I know it's getting towards the edge of the screen maybe, but we don't need much room for this. 0x component, 0x component, possibly positive x component. We don't know how big it is, but I'm just going to call it the unknown magnitude f of the friction. Comes in with a plus sign to make it an x component. That's the only one with a non-zero x component. That's equal to 75 times ax. What's ax here? It's 0 because a points toward the center of the circle, and so it has 0 x component, right? So the friction force is 0 here. We allowed for it to be non-zero, but then we solved and it was 0, so that's okay. Questions on C before we amend it to just and see how things change for D. D, I believe, is at the top, right? Rounding the top. So D is position C in there, I don't know. But in any case, part D is as the person is rounding the top like that. So I'm just drawing a little cartoon to remind myself of the situation. As the person rounds the top, let me just talk about how to change perhaps this free body diagram. How about the weight force? Do I need to change that? No, still down if I'm drawing the same relative to this cartoon here. What about the scale force? Well, hopefully it's still pointing out. If you're going frighteningly fast, you might need a seat belt to keep you attached to it, but we're assuming, you're still, it's pushing up on you. Let's imagine there is no seat belt and your seat can't pull down on you. It can only push up on you, right? But normally we would run a Ferris wheel so that the seat has to still push up on you. We'll see what it ends up being. Okay, and the friction force, again, we're going to show it's 0, same exact argument as before. In fact, if I choose these same set of axes here, let's just do that for the sake of argument. I'm going to choose the same set of axes. Same exact argument shows that the friction force is 0, right? Because my only thing that needs to change is A. Which way does A point here? Down toward the center of the circle, which at the top of the circle is down. So I'm just going to draw it there. Notice if I'm keeping the same axes, now AY is negative, right? AY is negative because if I keep my same axes, I've chosen, and I'm allowed to do that, plus Y is up. Now AY is negative. Okay, so let's change this now. Fy, the sum of the force y components, F still comes in with a plus sign. 735 still comes out with the minus sign. Nothing changes on the left-hand side, right? Mass of the rider, or mass in the free body diagram, still 75. What changes on the right-hand side? It's just that the acceleration, this is the magnitude of the acceleration, but its y component is negative. So you got to put in that extra minus sign just by knowing how it relates to the axes. And that makes all the difference, right? Because before when I added the 735 over here, something else positive was adding onto it. And now something's subtracting off of it, which makes your apparent weight less, or the scale force less. 130 newtons. So you would be feeling very light at the top, feeling like if it went a little bit faster, you might start to fly off this thing. So hopefully you've got a seatbelt on, or they're not going this fast. Yes, Hala. Sure. Well, let's see what happens there if anything changes. You are always free to choose whichever way is convenient for you to draw the axes. So if you choose plus y that way, what would change in here? Okay. Right, so everything changes sign in the whole equation, and that doesn't change anything in the equation, right? Overall, it's the same equation, just multiplied by -1, which has exactly the same solution. So it doesn't matter at all. In fact, if this were the first thing I were doing, I would have chosen plus y down just because, hey, I know the direction of the acceleration. Why make it have a negative component? But sometimes you forget, or sometimes you have good reasons for choosing it the other way, and you just got to remember to check the sign of the component. Okay, any questions on D? All right, now E is as you're rounding the side of it. So again, it's always good to draw pictures. Maybe here's our 75 kilogram rider in there, rounding the right-hand side, maybe heading upwards. We'll find out it doesn't really matter if they're heading up or heading down, since we won't use that piece of information. All right, let me adjust my diagram here. The weight force, still 735, right? Still down towards Earth. The scale, well, hopefully it's pushing up on you. And, the scale is also going to be the source of the friction here. But, when you have a scale, it's designed so that it only reads the downward component of the force. If you took something and pushed down on it with a certain force and then started pushing to the right, it wouldn't change the reading at all. It only cares how hard you're pushing down on it. It doesn't care if it's pushing to the right or to the left. So it's not going to register anything associated with this. It only cares in the direction perpendicular to the seat, assuming we're talking about a flat scale that's sitting on a flat seat like that. So this looks exactly the same. And just for the sake of argument, let's keep Hala's, because we can, all of the forces still horizontal and vertical, so it only makes sense to choose that horizontal and vertical. Which way is the acceleration in this case, by the way? To the left in my diagram, right? Toward the center of the circle. Good to draw it so that you get the sign of the component right. So in this case, let's redo F net y equals MAY, okay? In this new amended set of axes, F scale would come in with a minus sign because I'm choosing plus y is down. 735 would come in with a plus sign. The mass of the rider is still 75, right? This has 0 y component still. What's the sign of the acceleration now? What's AY in this case? It's 0. Because A now points that way and Y is down. So A's Y component is 0. I'm going from tail to tip. You don't have to move along the Y direction at all. So this is a big 0 over here. And notice when you solve this, that means F scale equals 735. You just have your normal weight in terms of how hard you're pressing down on the scale. You don't feel crushed into the scale or lighter than normal in terms of how you are on the scale. So that's the same as we got up at the very top of this problem. Well, something's got to be causing this acceleration, and the only other thing available is friction, right? It's the only force with a component along the direction of the acceleration, so it's got to be friction. So let's do the sum of the force x components equals max. I know I've got it squeezed in over here, but the only force is the magnitude of the force of friction, and I can see it's got to be pointing in that direction because the acceleration is resulting in that direction. So it comes in with a plus sign. That's equal to the mass of the rider. And in this case, with my chosen direction for x, A's x component is positive. 11 squared over 15, again, is the acceleration. Uniform circular motion, that's how fast you're accelerating toward the center of the circle. And that's how I computed that 605 Newton friction force, presumably. Okay, so as you're going around, as you're going around this part, you're feeling shoved in that direction by friction, right? Your seat is tugging you toward the center of the circle. As you go around the top, you feel light, but no friction force. As you go around the bottom, you feel crushed toward the bottom if it's going this frighteningly fast. Okay, that's about as complicated as it's going to get in this class because we've got something moving in uniform circular motion, but the forces are actually changing a lot as you go around. Much more than they were in the conical pendulum. Any other questions, follow-on stuff for this? Yes. Yes. That's right. It would have X and Y components if I chose these same axis directions. You know, we'd have to think about it, but yes, you know, you might be able to choose tilted axes. It just depends on what kind of information you know there, but it would probably be best to choose tilted axes where along the direction of the acceleration at some point in between there, so that one of the axes would point along the acceleration. So if you knew what angle, you know, if you were 30 degrees beyond the bottom, then one of your axes should be tilted at 30 degrees away from the vertical. That's going to be yet a more difficult kind of problem. Okay, let's go back to the slides if there are no other questions on that one. That's it, you know, that's pretty sophisticated kind of problem. Okay, this is all the solution that was, if you watched the video, was shown in the video. Okay, here's the next question we're going to talk about. Well, let's do this here. I brought a cup. My usual cup had been cracked, so I had to rig up another cup here. But let's put some water in a cup, and I'm going to swing it in a circle. And it seems sort of magical in that the water's not going to fall out of it. If you've done this before, you have a good intuition about how to make the water not fall out of it. Hopefully my whole thing is stable enough here. But you know you can't do it too slowly if you're going to make it all the way around, okay? But I have a pretty good intuition about if I go fast enough, I don't want to go too fast because I don't want to break this either. But if I go fast enough, it's upside down and somehow the water is not pouring out of it. So that's something we can kind of hold on to. But the question we're asking here is, it's pretty clear to most people that if I don't do a large enough speed as it's going around the top, it might sort of stall out up there. And then the water, you know, the string would become, you know, lax, dump the water out, and I'd be out of luck, right? So there's some minimum speed. Going too fast, as long as everything doesn't break, whipping it around just means it's going to be really taut and the water really won't fall out. But there's some minimum speed at which I can swing it. The speed we're interested in is the speed at the top. How fast does it have to be going around the top so that the water stays in the cup when it's upside down? Here's a sort of analogous thing that at least when I was a kid, I played sometimes with Hot Wheels, or here's like a mass on a frictionless loop, the loop kind of thing. And somehow it's upside down and the track is actually pushing down on it, and yet it's staying on the track. Same kind of idea. Why isn't it falling off the track? Here's my Hot Wheels car going around. Some years ago, someone actually did this in a car, and it's, you know, you can see the video on YouTube, of course. And it actually was he had to be very careful with it, because if human beings get pulled down, feel too many G forces, as we call them, right? Your apparent weight is much bigger than your normal weight. You can pass out because the blood sort of goes away from your brain, and you don't want to be passing out if you're driving a car on the loop-the-loop. So he had to go fast enough that he could make it all the way around, but not so fast that he felt when he was toward the bottom of it that he, you know, blood rushed out of his head and he passed out. So there was kind of a narrow range of speeds, but he did it. Of course, he did his calculations ahead of time and practiced a lot before he did it. All right, so let's think about this. We're concerned with someone going around in a circle. If you like, you can think of them as going at constant speed. You know, the car here is actually going to slow down as it goes up, but we're only concerned with what's happening at the very top. So we're going to consider something moving at speed v. Speed v is pretty constant as it's rounding the top. So we'll say, at least for this short little period here, it's in uniform circular motion. And of course, what I want to do is draw a free body diagram. If I want to know a minimum speed, that speed's going to come from v squared over r. That's an acceleration, and the acceleration is going to appear in F net equals ma. And in order to use F net equals ma components, I have to draw a free body diagram showing the forces and then put axes on it. Okay, so let's first imagine your intuition as you're in this car and you really whip around fast. What sort of forces are you going to feel there? Are you feeling, well, Let me just throw it out to you guys. Certainly gravity, you know, yes, gravity is going to be pulling down on me, no doubt. Gravity is pulling down on me, but what other forces are there? Let's suppose I'm sitting on a seat. Is the seat pulling on me upwards, or is it pushing on me downwards as I'm upside down rounding the top? It's pushing down on me downwards, right? You may have the intuition that as you go around the top, you're going to feel crushed upward, right? So the car is being pushed against the track. It's pushing on the track upward. That means the track is pushing on the car downwards. And so the free body diagram, of course, not only includes the weight, let's call this the mass of the car. It wasn't exactly clear here, but if we follow this little picture here, M is the mass of the car. So we've got the weight of the car going down, but we've also got, as it's passed, if I'm drawing a free body diagram at this instant, the track is pushing down on it, which is sort of counterintuitive. If everything's pushing down on it, why isn't it falling off? I mean, it seems like all the forces are in that direction. We've got to think about that. Okay, now, if you're moving at a very fast speed, of course, v is really big, so v squared is going to be huge, and v squared over r will be a large acceleration. You're going to be accelerating downward at a great rate. Okay, no problem with leaving the track there. If I need a big resulting acceleration, that means I need a big F net along that direction, and those two forces are going to provide it, right? Big acceleration, because v is big, means I need a big net force. They seem to all line up there. Now let's imagine we slow it down a little bit. So we're going only at a somewhat fast speed. The acceleration vector, you may not have noticed it got a little bit shorter. That means these two forces can't add up to as much. Now, can mg get any smaller to make the net force smaller, to result in a smaller acceleration? No. When you're near the surface of Earth, mg is what it is. Your weight is always going down. So you'll notice in my free body, well, let me back up. See, between these two, as the acceleration gets smaller, mg stays the same. Your weight's always the same. What's the only thing that can adjust? Well, it's the force from the track. You may have that intuition that you're going to feel crushed towards the track, but as you start slowing down, you won't be so crushed towards the track. The track's not pushing down on you as hard by Newton's third law. Here's an even slower speed. mg is the same, track force gets smaller. If I get to the minimum speed right here, the bare minimum where I'm just going to barely stay on the track, that downward force from the track is going to go to 0. And if I wanted to go to a slower speed, again, we're just calculating the acceleration length from v squared over r. If I tried to go around slower, the acceleration vector would have to get smaller. And this force was already perfect to make that acceleration vector before. The only way for it to get smaller would be if the track starts pulling up on the car. My Hot Wheels car doesn't have any way for the track to pull up on it as it's rounding the top. The track can only push down on it. It can't pull up, right? If you were on a roller coaster, of course, then there's rails that can actually hold you up, and so you won't fall down. It can pull up on you. But for a car rounding, you know, loop the loop, there's no way for this to happen. The track actually can't physically exert a force up on the Hot Wheel at that point. Okay, so the minimum speed corresponds to when the downward force from the track goes to 0. And it's the same way for this cup of water. If I swing it around so that as it's passing the top, the only force on the water is not a downward force from the cup, but just the weight of the water, is the perfect force to cause the needed acceleration to keep it on that circle, v squared over r. Then that's going to that v that corresponds to that will be the minimum speed. So here's my free body diagram. Again, I've left out the other force because we're only drawing the free body diagram that corresponds to the minimum speed. And there's only one force acting on it at the top. It's the weight force. The track force has gone to 0. And in order to use F net equals ma, I had to choose an axis direction. Why not choose it towards the center of the circle, right? Otherwise, you're just making work for yourself. So I'm going to choose plus x to be down, and then do F net x equals max. The only force available, and it's all along x, is mg, and that's equal to the mass in the free body diagram, just calling this car's mass m, times v squared over r, and that v is going to correspond to the minimum because the forces I drew corresponded to the minimum. So I'm calling it v min squared over r. I know it's kind of small for those of you in the back there. But notice the m's cancel out in that equation. And then I can solve for v min. And when you do that, you get the square root of gr. So that minimum speed just depends on the radius of the track. Little g is a constant, but as the radius of the track gets bigger, the minimum speed gets bigger, not surprisingly, right? Big loop the loop, you have to go faster around than a little Hot Wheels track kind of thing. Okay, that's just a little side calculation, but another example of F net equals ma. Any questions on that one?
I got a question.
Yes.
So like, what happens to F track? Does it become 0?
Yeah, I'm drawing a free body, I can draw the free body diagram for different conditions. And if I'm going at a very fast speed, F track is there, right? I'd say I've got to make an acceleration which has length v squared over r. So the bigger v is, the bigger F net I require. And these two forces have to add up to the net force going downward. mg is what it is. So the track force is going to adjust itself to give the required net force to keep it on the track and keep it going in a circle with v squared over r acceleration. As you slow down, mg stays the same and F track gets smaller. And when you're at that critical minimum speed, where I'm going as slow as I can up here, and that's the case I want to draw the free body diagram for, that downward track force goes to 0.
So because acceleration is 0?
No, the acceleration is not 0 because I'm still going in a circle. When I'm swinging that water around, even at the minimum speed, if it just barely makes it around without falling out, it's still going at a perfectly finite speed. And that means v squared over r is going to be something perfectly finite. So this is a nice non-zero acceleration here. But this weight force is just the perfect force to provide that acceleration. They're both along the right directions. And this is just the perfect force to cause that acceleration. If I needed to accelerate more, I'd need to add another force on top of it because mg can't change. But I can't make this acceleration any smaller. And by going more slowly, I'd have to make the acceleration smaller because v is getting smaller in v squared over r. Right? And if I made it any slower, in order to have a shorter acceleration vector, I would need an upward force to cancel against the mg force that's there. Grant, feel free to follow on with a question if you want.
No, I get what you're saying. Like,
is that good? Okay.
It's like the perfect force where it would
yes, at that critical
out.
speed, it is the required F net that gives that A along the same direction.
Got it.
Okay. Let me just mention one more thing and then we'll stop and talk about the exams. There's a discussion in there. This is a case where when I'm swinging this thing of water around in a circle, it's not actually in uniform circular motion. You probably know that as your Hot Wheels car goes up the track, it's actually slowing down as it goes up. So that's a case of not uniform circular motion, but non-uniform circular motion. Same thing when I swing this thing of water around. And so there was a section you read, I think, in this group of sections, that was called non-uniform circular motion. And the upshot is just this. This is the takeaway message. If I'm moving on a circle of radius r, but now my speed is changing as I'm going around, right? So you're not moving at constant speed anymore. The acceleration component towards the center of the circle is the same as it was before. In other words, whatever my v is at that instant when I'm on the circle, my acceleration at that point my acceleration component along this radial direction is that speed squared over r, the radius of the circle I'm at. What changes is that there's also another component to the acceleration vector, which is along the tangent direction. So we might call the two axes I've drawn here, I could have labeled them x and y, but I've oriented one along the inward radial direction. I called that the r axis. and one along the tangent direction to the circle. I call that the t-axis. And I believe that's somewhat similar to what Giancali does. And so the tangential acceleration, which appears in the case of non-uniform circular motion, just tells you the rate at which the tangential velocity is changing. So if I'm moving around in a counterclockwise direction and I'm going faster at this point as time goes on, I need a component, a positive component of acceleration along the direction I'm moving to speed me up. So a tangential would be positive there. So as you're moving down, maybe, I don't know that I necessarily want to do this now because I want enough time to talk about the exam, but maybe just a quick picture, and that is this. If I imagine I'm a car going around a loop like this, as I'm rounding the top, I was slowing down all the way to the top, and then I start speeding up all the way to the bottom. So I'm neither speeding up nor slowing down there. And that means the direction of my acceleration is all along the direction towards the center of the circle. I don't have a tangential component because I'm not changing my tangential speed. As I start down here, I'm actually speeding up along the direction I'm moving. And that means not only do I have a component of my acceleration toward the center of the circle, but I've also got a component of acceleration along the direction that I'm speeding up. And so my acceleration vector is actually not going to point along the radial direction anymore, but the radial component of it is still going to be v squared over r in length, where v is whatever the v is that I have right there. Might be different than what I had at the top because I sped up a little bit, right? So you just use whatever v you have at that point. Okay, yeah, so let's stop with the material there and let me pass back the exam. It didn't